This module explains the basic property requirements for three-dimensional models to ensure they deliver the Environment Agency asset management needs. This module will cover the link between project information models developed during project delivery and the Environment Agency's asset information model that is used in operational asset management, how three-dimensional model objects are to be segregated and classified, and the level of definition of graphical models and how this evolves throughout the project lifecycle. Project information models developed during project delivery require information to be consistent and in a format that allows it to be transferred into our asset information model. The transfer of information between these information models is via GeoCobi datasheets at project gateways. GeoCobi datasheets are an efficient way of transferring large sources of information into the asset information model and ensuring it is delivered in a standard format. The CAD Object Standard set out the requirement for the properties of graphical models, for example the way they are constructed and how information is stored within them, to ensure they can be broken down into GeoCobi files and ultimately fulfill our asset management needs. In order to deliver consistent three-dimensional models, the standards require the following: a clear breakdown of larger models into a series of submodels that can be delivered by different disciplines, which can easily be federated together to form the whole model. Further subdivision of objects into features and elements that are classified in accordance with the Environment Agency's Data Requirements Library. Standardized geometry, including units of measurement, symbology and material hatching, to ensure models can be federated accurately and look the same. And that attribute information is embedded within graphical objects in a consistent manner, so that it is transferable between information models. Now we will look more closely at object classification. The other topics will be covered later in this training module. The breakdown of objects within graphical models follows the Uniclass and Data Requirements Library system that is outlined in the Naming Convention and Layering Standard in Training Module 2. Objects are subdivided into two different categories, features and elements. Here we have an example of a simple culvert, which is classified as a feature. It has been given an asset reference of CS0001 and assigned a human readable name of Simple Culvert 01. The asset reference follows the format defined in the Data Requirements Library, assigned to a simple culvert. The name is a customizable entry used to easily identify the feature. The feature represents an asset type which can be broken down into smaller components called elements. Guidance for what elements to use to make up a feature is also defined within the Data Requirements Library. In our example, there are several elements associated with the culvert feature. Two aprons, both upstream and downstream, a head wall at both ends of the structure, and finally a culvert connecting the two head walls. The feature and element codes are recorded in attribute data cards linked to each graphical object, along with other asset information. This process can be applied to all types of Environment Agency assets and is a way of ensuring consistency of asset definition within the asset information model. The amount of information stored within models is known as the level of information. The accuracy of the geometry, composition of objects, and their aesthetics is known as the level of detail. These combine to become the level of definition, or LOD, of the model. We'll cover these in more depth in the modules on geometry and attribution requirements. As a project progresses through each stage, from concept to construction and handover, graphical models will develop to provide greater detail and contain more information. These combine to deliver an increasing level of definition appropriate for each stage of the project lifecycle. In this module, you have learnt about the importance of applying the CAD and object standards to graphical data in project information models to ensure that asset information model meets asset management requirements, how three-dimensional model objects are to be segregated and classified, and how the level of definition of graphical models evolves throughout the project lifecycle. For more information on how features and elements are to be named, visit the Environment Agency's Data Requirements Library. Functional requirements address the way graphical models and objects operate, ensuring they do not become too big or complicated, which would make them difficult to use. This module will explain model landing pages and how they provide quality and security controls for models, file workability requirements, looking at how well model files function, the purpose and requirements for interoperability, and a simple overview of what parametric modelling is and what the benefits are when used to create graphical objects. All models must contain a model landing page to describe what the model is for and what it contains. It also controls any revisions that are made to the model throughout the project and operational life cycle. Standard forms are provided in the appendices of the CAD and object standards. A security classification field is provided on the model landing page with a drop-down list of options that are aligned to the government security classification system. Sensitive data that is being used within a project should be segregated into separate models, assigned an appropriate security classification, and managed accordingly. The Employee's Information Requirements provides further guidance on how we should deal with sensitive digital data on our projects. Workability of models is essential for ensuring files can be managed and operated in a timely manner. It means making it easier to work with models by keeping the file size down. We do this by using federated models. Model federation is where smaller models are created in separate files. These files can contain models per discipline, such as a civil engineer or a mechanical engineer, or a project feature or asset, such as a fish pass or a weir structure. Models may also be created to segregate secure or classified data so that it can be controlled in the right way. These separate files are brought together in the federated model file, where each can be reviewed against one another and the design process coordinated from a single source. Keeping model memory sizes to a minimum is important, as this avoids slow speeds when viewing or amending the files. A guide to file size limits is provided in the Environment Agency's Employers' Information Requirements. Interoperability is the ability for a native file, such as an AutoCAD drawing file, to be read by other software applications, such as Navisworks. To enable this, native design files need to be exported into an interoperable file format or open format, such as IFC Industry Foundation Class, or IFC for short. Interoperable file formats can be opened in a federated model to enable all stakeholders on a project to amend or review the information. It is important that interoperable files retain both graphical detail and embedded information within the model. Interoperable file formats can be read by most CAD applications, which means stakeholders will not need to purchase new software. Parametric modelling is a tool within drawing applications that creates smart objects. A parametric object is one where its size and appearance in the model is defined by setting one or more parameters in the CAD software. Parametric fields can include geometry, materials, and finishes. By adjusting the settings of each parameter, the appearance or shape of the object can be changed very quickly compared to redrawing it. In this example, we have a cross-section of a simple embankment. The object has been assigned parametric fields for crest width, slope gradient, and material type. If we were to alter these parameters, the model changes automatically to reflect the new values assigned to each parameter. Parametric modelling principles can be simple and very effective when applied to CAD model production processes, saving time and providing consistency. In this module, you have learnt about model landing pages and how they provide quality and security controls for models, the importance of file workability to ensure models can be used effectively, how interoperability is important to allow collaboration across different stakeholders, and how parametric modelling can provide efficiencies when producing models. The geometry requirements of the Object Standard provide guidance for the aesthetics of three-dimensional models and how objects are presented. This module will explain level of detail of graphical models and how this develops through a project life cycle, how units of measurement are standardized and assigned to models, the use of standard 3D symbology to replicate the two-dimensional symbols used in drawings, and the use of standard materials and hatching for three-dimensional objects. Level of detail is one component of the level of definition of a graphical model. The second component is level of information, which shall be covered later in this training module. Level of detail represents the level of accuracy in geometry, the composition of objects, and their aesthetics. The Environment Agency follows the REBA 7-stage plan of work for delivering projects. This separates each phase of the project life cycle from strategic assessment through design, construction, and operation of the asset. Between each stage, decisions are made on how to proceed to the next stage. Graphical models provide key information to guide the decisions that are made at the end of each stage. Therefore, the level of definition corresponds to each stage of work, so that there is a common understanding of how much detail and information is required in a graphical model at each stage. The CAD and Object Standards provide guidance on the level of detail, typically required at each stage, with the geometrical model becoming more refined and realistic with the project life cycle. To ensure that all graphical models align with each other in the Asset Information Model, the CAD and Object Standards specify the units of measurement that should be used. These are confirmed within the Project Information Parameters table within the drawing file, which provides information for the GeoCobi datasheets. Another aspect of geometry requirements is the use of symbology in a three-dimensional environment. The Environment Agency Object Standard provides a library of three-dimensional symbols to be used in models to replicate the two-dimensional symbols used on drawings. "3D model versions can cover various aspects and disciplines, including items such as setting out symbology, construction hazard symbols, geotechnical ground investigation symbols, environmental constraints and habitat identification symbols, and general model information such as gradients and falls. Multi-view objects are a good method of using symbology for both drawings and models. These functions in the modelling software enable an item to be viewed differently depending on its orientation. In this example, the hazard symbol on the left is being looked upon in a plan view. This displays a two-dimensional symbol, ideal for use within a drawing. When the same object is being looked at in an isometric view, as shown on the right, it is displayed as a three-dimensional symbol. This allows a one source of the truth approach, eliminating the need to replicate the same data to view files in different dimensions. Finally, geometry requirements focus on how materials are presented in a three-dimensional environment. The CAD Standard outlines how to display materials in a two-dimensional format in the form of hatching. The Object Standard outlines how these are to look in a three-dimensional model through rendering. A library of materials for Autodesk and Revit software platforms is provided as part of the CAD and Object Standards. In this module, you have learnt about how the level of detail of graphical models develops through a project lifecycle, how units of measurement are standardized and assigned to models, how 3D symbology should be used to replicate the two-dimensional symbols used in drawings, and the use of standard materials and hatching for three-dimensional objects. The final component of the Object Standard is the attribution requirements. Attribution is the information hosted within a model that allows different models to be linked and referenced consistently. This module will explain what data attribution is and why it is needed, level of information of graphical models and how this develops through a project lifecycle, the criteria for attaching data to ensure it can be shared across many software platforms, and what data is required to be included within models. Data attribution allows information about assets and products to be stored within graphical model objects. This could include data such as the manufacturer of the product, the manufacturer's model ID or reference, costing associated with the initial purchase and future replacement, carbon and sustainability information, material information such as finishes and grades, the product or asset's lifespan, warranty information such as duration, or any specific features associated with that model. The amount of data that can be attached is unlimited. However, data attribution should be used sparingly and aligned to the project and asset management needs. This is defined in the GeoCobi datasheets and the Environment Agency's Data Requirements Library to ensure the right information is received and that it is consistent. Level of information is one component of the level of definition of a graphical model, in addition to level of detail covered in the previous section of this training module. Level of information represents the amount or quality of data that is embedded within objects and graphical models. Looking again at the 7-stage plan of work for delivering projects, there is a corresponding level of definition that graphical models will have at each stage. The CAD and Object Standards provide guidance on the level of information typically required at each stage, with the model becoming richer with more useful information as a project develops. In the initial phases of a project, graphical objects are likely to hold only limited attribute data, such as a feature classification for each asset. Moving through the appraisal and outline design phases, objects will become more defined, with assets being broken down into individual elements and decisions made on what material they will be constructed from. Information attributed to these objects will help other processes, such as costing and carbon calculation. As a project reaches construction, a greater level of information is included, such as material specifications. For example, a linear defence may have been assigned the material type concrete in the outline design phase, which would be used to generate costing and carbon information for the project appraisal. Following detailed design, the construction model would also include the concrete grade and other specifications to enable the contractor to plan and construct the flood defence wall. Once construction is complete, additional data relevant to operational, maintenance and decommissioning phases is provided within the as-built graphical models delivered at handback. This could include specifications for products such as serial numbers, warranty information and installation date. No matter the software application used, model object data attribution needs to achieve the following criteria. Data delivered to the Environment Agency must be consistent, irrespective of the organisation that has created the model. Model data must be exported into a GeoCOBE datasheet for transfer from the Project Information Model to the Environment Agency's Asset Information Model. The data must be retained and viewed when the model is transferred to an interoperable format, such as an Autodesk Navisworks file. Information must be adopted by the Environment Agency in a way that further data attribution can be added to objects in the future. For example, additional maintenance records and details of servicing needs for assets. Key asset attributes such as classifications and asset referencing are provided in the Environment Agency Data Requirements Library. The library is divided into asset types or groups of similar assets, such as aids to navigation. Under each asset type is a list of common Environment Agency assets. These are called asset subtype, and each leads to a breakdown of feature attributes and elements. Each asset subtype or feature has a list of attributes that help to maintain and operate the asset in the future, such as its condition or public safety risk assessment rating. The attributes table also provides the range of acceptable values for each attribute, for example, yes or no, or a condition rating of 1 to 5. A GeoCOBE mapping code is provided to enable automated transfer of attribute data into the GeoCOBE datasheets. Each asset type or feature is further broken down into individual elements. In a similar way to features, each element leads to a table of attributes. These, like the asset type attributes, state the acceptable values and mapping code for the GeoCOBE datasheet. In this module you have learnt about what data attribution is and why it is needed, how the level of information within graphical models develops through a project life cycle, how attribute data should be attached to models, and where information required to be included within models can be sourced.